Okay, so here we are, and we're going to simplify. The limit as n goes to infinity, so if I look at the alternating term, I'm left with minus 1 to the 1 power. This term and this term, I'm left with x minus 1 in the top. This term and this term, I'm left with the 2 to the first power in the bottom. And this term, now that I've got it right, is n over n plus 1. So if you recall what we talked about earlier, we said anything not involving n gets moved out front. So we're going to take the limit as n goes to infinity of the absolute value of minus 1 x minus 1 all over 2, the limit as n over n plus 1 as n goes to infinity. We should have done enough of these before to know that this goes to 1. We're going to be multiplying that by, now I am going to distribute this negative term here, so this becomes minus x plus 1. And this times 1 has to be less than 1 to converge. So now what I'm going to do is, I'm going to come up here. So I'm going to rewrite this without the absolute values. So this becomes minus 1 has got to be less than minus x plus 1 over 2 less than 1. Now I'm going to multiply everything by 2. So this becomes minus 2 is less than minus x plus 1 is less than 2. Then I'm going to subtract 1 everywhere to get x by itself. So this leaves me with minus 3 is less than minus x is less than positive 1. And now, in order to get x by itself, I have to divide everything by minus 1. And if you remember your rules of inequalities, that is, anytime you multiply or divide by something negative, you have to flip your sign. So this becomes 3 is greater than x is greater than negative 1. So this is our interval of convergence. Now I'm going to show you a shortcut. Your book tries to explain this right out of the box, but I feel strongly that kids don't know what the heck's going on if you try to show them it right from the beginning without doing some work with finding intervals of convergence yourself. Now, you were told earlier in the problem that I have to find it. You were told that the radius of convergence is 2, correct? If you are told the radius of convergence, and you're told you have a Taylor series about a number, or even if you have a Maclaurin series, you can find the interval of convergence this other way. So if you know this, and I'm told it's a Taylor series about x equals 1, then I can write this. I can say the absolute value of x minus 1 has got to be less than 2. It's got to be less than the radius of convergence. And I can go ahead and just solve this. So this becomes minus 2 less than x minus 1 is less than 2. Get x by itself, add 1, add 1, add 1. Minus 1 is less than x is less than 3. So that is a shorter way to find it. But you can only do this if you know the radius of convergence. If it had been a Maclaurin series, what would be different here? It would just be x. Good. Very good.
Is it always x plus 1, or is it whatever the x is equal to?
Right.
So if it's at about...
Right, because the general formula for this is x minus a less than the radius of convergence. And you're told that it's a Taylor series about x equals 1. So when they say x equals 1, what they're really giving you is a. Are we done with that one? Yes, sir?
Yes.
Okay. Thankfully, the next two are pretty quick. After all that, and here I thought I was going to have enough room. All right, so let's pull the sheet down. And it says, the Taylor series for the function about x equals 1 can be used to represent a function 1.2. Remember, if they're going to ask you to evaluate a function around a different value, it's got to be close than this a, it's got to be close to this a value. They're not going to ask you to find f of 4.7. That's too far away from this a value, and this won't approximate well. All right, the Taylor series for f about x equals 1 can be used to represent f of 1.2 as an alternating series. Use the first three non-zero terms of the alternating series to approximate f of 1.2. So all they want you to do is take these first three terms and plug in 1.2 for x. That's it. So it's a lot of words for something that's actually pretty easy. So we're just going to say f of 1.2 using the first three terms would be 1 minus 1/2 times 1.2 minus 1 plus 1/8 1.2 minus 1 squared. This is a no calculator problem. So you should be able to take these numbers and work with them. Now my recommendation is to convert everything to just fractions, because I found that to be easier. So those two cancel, so I've got minus 1/10 plus 1/8 times 4 over 100 equals 1 minus 1 over 10. That goes into that twice. Plus 1 over 200. Now, if you don't know what 1 over 200 is, take 200, go into 1. 0.005. I think that's right. 0.005 times 2 is 10. I think that's right. Let's hope so. So this is 1 minus 0.1 plus 0.005. Close enough. Part D. Show the approximation found in Part C is within 0.001 of the exact value of 1.2. So this is basically asking us to find the n plus 1 term. Back up. I'm sorry, what?
That's what I meant, sorry.
Okay, so what we're going to do for Part D is we are going to calculate the n plus first term using the general term. So we're going to do something like this. We say the absolute value of the difference between the function and the polynomial is guaranteed to be less than we're just going to take the absolute value of what we get for the third term. So if you recall, when we talked about error, we said a function is made up of the polynomial plus the error. Or maybe I shouldn't say it like that. The polynomial, our first three terms, plus everything else